Welcome to all. Today we are here for the concept of directional derivatives. First we will know how the concept of directional derivatives came into existence. It is because of the fact that when a function is in the plane or is in space, then it has many directions with respect to points of the domain. Which may be plane or space. Thus, we need to study change the function values along different directions. Which lead to the origin of concept of directional derivatives. Hence, so we can note it as directional derivative is defined for functions with multiple variables. Here the variables are greater than or equal to 2. Now let's see the literal meaning of directional derivatives. So literal meaning says derivative of the function along a particular direction. Means rate of change of the function along a particular direction. This is about the literal meaning of directional derivatives. Now let's see the formal definition of directional derivatives. The definition: let f be a differentiable real valued function on E3, as we are studying the whole concepts on E3 space, and let Pp be a tangent vector to E3, then the number Vp of f is equal to d by dt of f of p plus tv at the point t is equal to 0 is called the derivative of f with respect to Vp in the direction of the vector part V. So this is a formal definition of the direction derivative. It says the direction derivative is nothing but d by dt of f of p plus tv at the point t is equal to 0. This is the direction derivative of the function f in the direction of vp at direction derivative of f with respect to the tangent vector vp along the direction of the vector part v. So this can be viewed as, so suppose this is a function f in E3. If it is a point of application P, I will take it here so that I can write the tangent vector. So this is the tangent vector VP, which is the point of application P. Here there may be the point V may be here. So this is the direction of V. Now the direction derivative of F is nothing but the change in F with respect to VP, the tangent vector, along the direction of the vector part V. Now let's see an example so that the concept is somewhat clear. Example says, compute Vp of f when f is equal to x square yz with the point P as p equal to 1, 1, 0 and the vector part V as 1, 0, -3. So now let's use the formal definition of the direction derivative and we will find the direction derivative Vp of f. Since Vp of f is equal to differentiating with respect to t with the function f of p plus tv at t is equal to 0. Now f is equal to x square yz. P plus tv is equal to 1, 1, 0 plus t into 1, 0, -3. So this is equal to 1 plus t, 1 minus 3t. Therefore, f of p plus tv is equal to x square means 1 plus t whole square, y means 1 and z means -3t. So this is equal to -3t into 1 plus t square plus 2t. This is -3t minus 3t cube minus 6t square. So this is about f of p plus tv. Now differentiating f of p plus tv with respect to t. So this will give -3 minus 9t square minus 12t. Therefore, d by dt of f of p plus tv at t is equal to 0 will be equal to -3. Hence, the direction derivative of the function with respect to the tangent vector Vp along the direction of V is equal to d by dt of f of p plus tv at t is equal to 0 will be equal to -3. So this is how we will find the direction derivative of the function by using the formal definition. Sometimes the formal definition of a direction derivative needs somewhat long procedure. Therefore, there is a formula to find the direction derivative without performing all the traditional steps, so which can be given in terms of theorem. So let's see the theorem. So it says, if Vp is equal to V1, V2, V3 with respect to the point P is a tangent vector to E3, then Vp of f is equal to summation Pi dou f by dou xi at the point P. So it says the direction derivative of f can be found out by knowing the coordinates of the vector part v and partial derivatives of the function f at the point p. So let's see how it can be proved. So first we use the traditional direction derivative for definition and we will arrive at the formula. So first we will consider p plus tv. So this is equal to p1, p2, p3 plus t. V is v1, v2, v3. So p is the point of application, v is the vector part. p1 plus tv, p2 plus tv, p3 plus tv. Therefore, f of p plus tv is equal to f of p1 plus tv, p2 plus tv, p3 plus tv. Now, we have to differentiate f with respect to t. So, d by dt of f of p plus tv is equal to dou f by dou x of f of p1 plus tv, p2 plus tv, p3 plus tv into, so with respect to x means so it includes the first coordinate. This is v. This is v1, v2, v3. So this is v1 plus dou f by dou y of f of p plus tv, p1 plus tv1, p2 plus tv2, p3 plus tv3 with respect to y means v2 plus dou f by dou z f of p plus tv, f of p1 plus v1, p1 plus tv1, p2 plus tv2, p3 plus tv3 multiplied by v3. So this I can write this as summation dou f by dou xi for I is equal to 1 to 3 f of p1 plus tv1, p2 plus tv2, p3 plus tv3 multiplied by pi. So because I am writing dou of xi, because I am taking x as xi, x1, y as x2 and z as x3. So therefore I can write d by dt of f of p plus tv by this expression. Now as the definition says, d by dt of f of p plus tv at the point t is equal to 0 will give the direction derivative. So this is equal to 1 to 3 dou f by dou xi f of p1, p2, p3 into vi. So this can be written as I is equal to 1 to 3 dou f by dou xi dou by dou xi of f of p into vi. Thus Vp of f is equal to d by dt of f of p plus tv at t is equal to 0. This will be is equal to 0. This will be equal to summation from I equal to 1 to 3 dou by dou xi of f of p multiplied by pi. So this is how we will get the formula for direction derivative in terms of partial derivatives of the function at the point p along with the coordinates of the vector part v. So to check whether the relation is true or not, we will Consider an example which was the previous one. So we have f is equal to x square yz, p is equal to 1 comma 1 comma 0 and v is equal to 1 comma 0 comma minus 3. Now first we find dou f by dou x is equal to 2x yz, dou f by dou y, this is x square z, dou f by dou z, this is equal to x square y. Now so dou f by dou x for the point P is equal to 2 into 1 into 1 into 0, this is 0. Dou f by dou y at the point P is equal to 1 square into 0, this is 0. Dou f by dou z at the point P is equal to 1 square into 1, this is equal to 1. Now from the theorem, Vp of f is equal to summation I is equal to 1 to 3 dou f by dou xi at the point P multiplied by Vi. So this is equal to dou f by dou x1, or I can write V1 plus dou f by dou x2 at the point P V2 plus dou f by dou x3 at point P to V3. Yes, we are taking x1 as x, x2 as y and x3 as z, then we have, so this is equal to 0 into V1 means 1 plus this is 0 into V2 means 0 plus this is 1 into V3 means minus 3. So this is equal to minus 3. So we can check this is true. Then we have used definition of direction derivative. So this was the earlier case, hence both are the same, hence the result holds. So this is, now we can find the direction derivative without using the actual definition, but in terms of partial derivatives of f at the point P and the coordinates of the vector part. Now we will see some properties of notion of direction derivatives. So it is given in terms of a theorem which says let f and g be functions on E3, Vp and Wp are the tangent vectors. A and B are the real numbers or any scalars from the real field. Then so A into tangent vector Vp and B into tangent Wp, the linear combination of tangent vector, and we are performing the direction derivative of f with respect to the linear combination of tangent vectors Vp and Wp. This is equal to A into Vp of f plus B into Wp of f. So next one, Vp of linear combination of functions here, this is equal to A into Vp of f plus B into Vp of g. And the next one is due to the product of functions f and g, this is equal to Vp of f into Gp plus f of p into Vp of g. So we will see how these results can be proved. So let's see one by one. So by the definition of the direction derivative, we have summation from I is equal to 1 to 3 dou f by dou xi at the point P into Vi. Now applying the same for the first one. So taking, instead of we are taking AVP plus BWP of f. This is equal to summation I is equal to 1 to 3 dou f by dou xi at the point P. Instead of Vi we are having A Vi plus B Wi. So this can be rewritten as I is equal to 1 to 3 A into dou f by dou xi at the point P into Vi plus summation I is equal to 1 to 3 B dou f by dou xi at the point P into Wi. So as A is not involving the ith term, so I can take A out. I is equal to 1 to 3 dou f by dou xi at the point P into Vi plus I, B is taking out. I is equal to 1 to 3 dou f by dou xi at the point P multiplied by Y. So from the definition of directional derivative in terms of partial derivatives, this can be written as Vp of f. Similarly, so this can be written as Wp of f. This is how we will prove the first property, which is in terms of linear combination of tangent vectors. So second one, it's about linear combination of functions. So by the definition of tangent vector in terms of partial derivatives, I can rewrite this as dou af plus bg dou xi at the point P into Vi. So this is the term wise partial derivative. I is equal to 1 to 3 A into dou f by dou xi at the point P plus B into dou g by dou xi at the point P 4 multiplied by Vi. So this is equal to I is equal to 1 to 3 A dou f by dou xi at the point P multiplied by Vi plus summation I is equal to 1 to 3 B into dou g by dou xi at the point P multiplied by Vi. So as A and B are free from the enumeration I, so I can take them out. A I is equal to 1 to 3 dou f by dou xi at the point P into Vi plus B into I is equal to 1 to 3 dou g by dou xi at the point P Vi. So using the definition of directional derivative in terms of partial derivatives, so this can be written as Vp of f and this can be Vp of g. So this is how this property can be proved. So let's see the next property, which is about the product of functions. Again applying the definition of Vp of f in terms of partial derivatives, I equal to 1 to 3 dou of f into g by dou xi at the point P multiplied by Vi. This is equal to, using the product rule of partial derivatives, so I rewrite this as f into dou g by dou xi plus g into dou f by dou xi at the point P into Vi. So this is equal to I is equal to 1 to 3 f of P dou g by dou xi at the point P multiplied by Vi plus I is equal to 1 to 3 g of P dou f by dou xi at the point P multiplied by Vi. So yes, f of P and g of E are free from I enumeration, so I can take them out. F of P into I is equal to 1 to 3 dou g by dou xi at the point P multiplied by Vi plus g of P taken out. I is equal to 1 to 3 dou f by dou xi at the point P multiplied by Vi. So by the definition of Vp of f means directional derivative with respect to partial derivatives, we can write them as this is Vp of g plus this is Gp. This is nothing but Vp of f. So this is how the third property, which is the directional derivative of the product of functions, can be proved. So we have important things, so we will note them. For the natural frame fields, U1, U2, U3, on E3 we have Uy of f is equal to dou f by dou xi. So we will see how this can be. First we will take I is equal to 1, then we have U1 of P as 100 P. So therefore we have P as 100 and point P as arbitrary. Then we have P plus TV is equal to, this is P, P1 P2, P3 plus T into V can be 1, 0, 0 is equal to P1 plus T, P2, P3. Now f of P plus TV is equal to f of P1 plus T, P2, P3. Now d by dt of f of P plus TV is equal to dou f by dou x multiplied by 1 plus dou f by dou y P1 plus T, P2, P3. So with respect to y coordinate this is 0 because there is no t term, plus dou f by dou z P1 plus T, P2, P3. So with respect to z coordinate also t is not present. So this is equal to dou f by dou x at the point P1 plus T, P2, P3 multiplied by 1. Now d by dt of f of P plus TV that t is equal to 0 is equal to dou f by dou x P1, P2, P3. So this is equal to dou f by dou x at the point P. So for the u1 means it is along a natural frame field along x direction. So we have dou f by dou x at the point P. So if I take x as x1, then we can get u1 of f is equal to dou f by dou x1 at the point P. Similarly for the u2 is equal to dou f by dou x2 at the point P, and for u3 this is dou f by dou x3 at the point P. Hence for natural frame fields ui of f is equal to dou f by dou xi at the point P. This is how we will find the direction derivative of f at the point P along the direction of the natural coordinate functions x, u1, u2 and u3. Let's see one more result on the direction derivatives, which involves tangent vectors or the vector v. It says if x1, x2, x3 are the natural coordinate functions then v is equal to summation p of xi into ui, where ui's are the natural frame fields. And v is any vector field. So let's see the proof of this. Since any vector v can be written as the linear combination of the natural frame fields along with the natural coordinate functions, Euclidean coordinate functions vi's. Now consider vp of x1, the direction derivative of the natural coordinate function x1 at the point P along the direction of the P. So this can be written as I is equal to 1, 2, 3 vi dou x1 by dou xi at the point P. So this is equal to v1 into 1 plus v2 into 0 plus v3 into 0, because dou x1 with respect to x1 is 1, dou x1 with respect to x2 is 0, with respect to x3 is also 0. This is equal to v1 at the point P. Similarly, we can check vp of x2 is equal to v2 of p, vp of x3 is equal to v3 of p. I'm substituting all this in the equation 1. We can have v is equal to summation I is equal to 1 to 3. This is v of p is equal to 1 to 3 is vi. V of v1 is nothing but vi. This is equal to I is equal to 1 to 3. Instead of vi, we are putting vp of xi into ui at the point P. So this implies v of p is equal to summation I is equal to 1 to 3 vp of xi into ui of p. So as p is arbitrary, we can rewrite v is equal to I is equal to 1 to v of xi into ui. This is how the relation can be proved. It's all about the concept of directional derivatives and some of the results associated with the directional derivatives of the function. So how we can find the directional derivatives without applying the formal definition, which can be in terms of partial derivatives, and some of the theorems on the concept of directional derivatives. This is about today's class. We'll see some problems on the concept of directional derivatives. Till then, keep